So good morning, all of you. Today, we will explore a fundamental principle in thermodynamics known as the first law of thermodynamics, which is often referred to as the conservation of energy principle. This law establishes critical relationship between various forms of energy, including heat, work, and total energy. The first law of thermodynamics states that the energy cannot be created or destroyed. It can only change forms. This means that in any given process, the total energy within a closed system remains constant. Every bit of energy must be accounted for during any thermodynamic process. Now, understanding these energy forms is very much crucial in defining this first law of thermodynamics. Now, we know what is meant by heat. It is the energy transferred due to a temperature difference between systems. Work is the energy transfer when a force acts over a distance. And total energy indicates the sum of all forms of energy present in the systems, including internal energy, kinetic energy, and potential energy. Take an example of a falling rock. The diagram illustrates the first law of thermodynamics. Let's analyze. This rock is falling from a certain height. It possesses potential energy, which is calculated using the formula of mass multiplied by gravitational acceleration into height above the ground. As the rock falls, its potential energy is converted into kinetic energy, which is given by 1/2 multiplied by mass multiplied by velocity square. If we assume the air resistance is negligible, then no energy is lost during this process. The potential energy lost by a rock as it descends is equal to the kinetic energy which is gained as it accelerates towards the ground. This confirms the conservation of mechanical energy throughout its falls. Now, therefore, the first law of thermodynamics emphasizes that while the energy can change its form from potential to kinetic, it is always conserved within an isolated system. Understanding this principle is crucial for analyzing various physical processes and designing efficient systems in engineering and physics. Coming on next slide, which indicates what is the consequence of the first law of thermodynamics. The first law of thermodynamics has several profound consequences that are essential for understanding and analyzing thermodynamic systems. Let's explore some of these key implications. The first one is the total energy as a property. The first law establishes that the total energy is a fundamental property of a systems. This means that the total energy of a system is a characteristic that describes the system state at a particular moment in time. One important implication of this is the net work done in adiabatic process depends only on the state ends of the system. In an adiabatic process, there is no heat transfer between the system and its surrounding. Therefore, any change in the system's total energy must be due to the work done on or by the systems. Since the net work done depends only on the initial and final states of the system, it follows that the total energy is a state function. This means that the change in total energy depends not on the path which is taken by the systems, but also on the initial and final states. Coming on to the next, that is the total energy change in an adiabatic process. Now, as we know, the mathematical expression for the first law is given by the change in energy is equal to the net work done in case of a adiabatic process. Now, it is important to note that the first law does not specify an absolute value of total energy. It only describes the change in energy which is happening during that process. Therefore, we can arbitrarily choose a reference point of total energy, and this is similar to how we choose a reference point for potential energy in mechanics. At its core, the first law statement of conservation of energy, it asserts that energy can only change the form. It cannot be created or destroyed. This principle has far-reaching implications for how we understand and analyze the physical processes. Take a small example of heat transfer without work interaction. To illustrate this, consider a potato being baked in an oven. In this scenario, heat is transferred to the potato, but no work is done. If 5 kilojoule of heat is added to the potato, then the potato's total energy increases by 5 kilojoules. This increase in total energy is manifested as an increase in the potato's total internal energy, which leads to a rise in its temperature. In this example, no energy is lost. It is fully accounted for as an increase in the potato's internal or the total energy. This underscores the fundamental principle of energy conservation, which is there in the first law of thermodynamics. Let's now consider a more realistic scenario of heat transfer when there are energy losses to the surrounding. This example will further illustrate the first law of thermodynamics and the importance of accounting for all forms of energy transfer. Consider a scenario that the water is being heated in a pan. Now, as the water is heated in a pan on a stove, heat energy is transferred from the heating element of the water, causing the water's temperature to rise. However, not all the heat energy which is transferred from the heating element ends up increasing the water's temperature. Some of the heat is lost to the surrounding through mechanisms such as convection and radiation. To analyze this situation using the first law of thermodynamics, we need to carefully account for all the energy transfers. That is, the energy which is added to from the heating element to the water, which is the heat energy. Consider it as a 15 kilojoules. The heat which is lost to the surrounding accounts for 3 kilojoules. Now, to determine the total heat transfer to the water, we subtract the heat lost to the surrounding from the heat which is added to the water. So, the net amount of heat which is given to the water is 15 minus 3 is equal to 12 kilojoules. This means water only receives a heat transfer of 12 kilojoules. According to the first law of thermodynamics, the increase in the water's total energy must be equal to the net heat transfer to the water. In this case, the increase in water's total energy is 12 kilojoules. This example confirms the first law that the total energy change of the water matches the heat transfer. No energy is lost. It is either stored in the water, increasing its internal energy, or it is transferred to the surrounding. We can use a simple equation for this. The heat which is there which is supplied is equal to heat which is stored plus heat which is lost. So 15 is equal to 12 plus 3. Now this simplified equation illustrates the principle of energy conservation. The total amount of energy entering to the systems is equal to the sum of the energy which is stored in the system and the energy that leaves the system, that is the heat loss to the surrounding. This reinforces the key message of the first law. Energy cannot be created or destroyed, only transferred or transferred. Now we will see one example of heating an adiabatic room. What is the adiabatic room? A room from which there will be no heat interaction from its boundary. Let's now examine a scenario involving an adiabatic system to further illustrate the implications of the first law of thermodynamics. An adiabatic system is one in which there is no heat transfer between the system and its surrounding. Consider a well-insulated room. Because the room is well insulated, we cannot assume that there is no heat transfer between the room and the environment. That is, the Q is equal to 0. In this scenario, the only energy interaction is the electrical energy, which is the work done by the heater inside the room. The heater is converting the electrical energy into thermal energy, which then increases the internal energy of the air in the room. Now, we have to understand how there is an energy transfer mechanism. So here, how the energy transfer process works is such that the electrical energy is supplied to the heater. Now, the heater converts the electrical energy into thermal energy. The thermal energy is then transferred to the air in the room, increasing its internal energy. Now, using this first law of thermodynamics, we have to understand the energy interactions. Since there is no heat transfer, Q is equal to 0, and therefore the first law of thermodynamics simplifies to the total energy change is equal to what is the work or the W electric system. Now this equation states that the change in the room's total energy is equal to the electrical work done by the heater. And this electrical work done by the heater is denoted by W electric. In other words, all the electrical energy supplied to the heater is converted into internal energy of the air in the room. This results in an increase in the room's temperatures. Now, we have to confirm that the first law has been satisfied. How it becomes? Now, this example provides a clear information of the first law of thermodynamics. The increase in the room's total energy is directly equal to the amount of electrical work done by the heater. This illustrates the principle of energy conservation. Energy is neither created nor destroyed. It is simply converted from one form. Here, there is an electrical energy into another form, that is the internal energy of the room. By understanding the first law and its implication, we can effectively analyze and design systems that involve energy transfer and transformation, ensuring that the energy is used efficiently and effectively. Now take another example, stirring a fluid in a adiabatic systems. This is another type of a practical example for analysis of first law of thermodynamics in action. This time involving adiabatic system with a paddle wheel used to stir a fluid. Now in this scenario, we have adiabatic system that is well insulated, meaning there is no heat transfer between the system and its surrounding. that is Q is equal to 0. This setup allows us to focus solely on the work interaction occurring within the system. Now, the paddle wheel is employed to steer the fluid inside the system. As the paddle wheel rotates, it performs shaft work on the fluid. This mechanical energy input from the paddle wheel is transferred to the fluid, resulting in an increase in the internal energy of the fluid. As a consequence, the temperature of the fluid rises due to this energy transfer. Since we have established that Q is equal to 0, that is no heat transfer, we can apply first law of thermodynamics, which simplifies to change in energy, that is delta E is equal to W, that is work which is done by shaft. This relationship indicates that the total energy of the system increases directly due to the work input from the paddle wheel. This example confirms the conservation of energy principle within a mechanical system. The increase in internal energy of the fluid, which results in a rise in temperature, is entirely attributed to the mechanical work done by the paddle wheel. No energy is lost, rather it is transformed from mechanical energy to thermal energy. By understanding how work contributes to change in internal energy in an adiabatic system, we gain valuable insight into how mechanical systems operate and how they can be optimized for efficiency. This reinforces our grasp of thermodynamic principles and their applications in the real-world scenarios. Now let's consider a common example of energy transfer and the first law of thermodynamics, that is the compression of air. This example will clearly illustrate how work is done on a gas and can lead to rise in the temperature. Now, air compression and energy transfer. This is a common example in thermodynamics. As we know, when air is compressed, its temperature increases. This phenomena is a direct result of energy being transferred to the air in form of boundary work. Boundary work refers to the work done on or by a system as its volume changes. Now, in case of an adiabatic compression, the heat transfer becomes 0. Therefore, if we assume for our simplicity that the compression process is adiabatic, meaning there is no heat transfer between the air and its surrounding. This assumption is valid when the compression occurs rapidly enough that there is not enough time for significant heat transfer to take place. In an adiabatic compression, all the work done on the air is stored as an internal energy. This internal energy is associated with the random motion of the air molecules. As the air is compressed, the molecules are forced into a smaller space, causing them to collide with each other frequently. This collision increases the kinetic energy of the molecules, which translates to a higher temperature. Now, since here we can modify the first law of thermodynamics by considering Q is equal to 0, therefore, the delta E, that is change in energy or total energy of air, is equal to the boundary work, W boundary. Since the total energy increase manifests an increase in internal energy, the temperature of the air rises. We take a everyday example of a bike pump. So everybody of you must be using a bike, and a common example of this is a bike pump. When you rapidly compresses the air in a bike, you will notice that the pumps get warmer. This is caused because as you do the work, it compresses the air and it is converted into its internal energy, causing the temperature of the air inside the pump to rise. The speed at which the gas is compressed is important because a fast compression won't allow much heat to escape, whereas a slow compression, however, will allow the heat to dissipate and the final temperature after the compression will be high. Therefore, by compressing the air, we are not creating energy, but rather converting mechanical energy into thermal energy, resulting a temperature increase. This provides a practical and a relatable example of the first law of thermodynamics in action. Now consider this case in which there is an energy transfer with heat and work interactions. So how energy transfers in a real world systems often involves both heat and work interaction, which are occurring simultaneously. Understanding this interaction is crucial for analyzing thermodynamic process accurately. In many practical scenarios, systems do not receive the heat or work. They experience both. This combined effect can significantly influence the system's total energy change. Now, consider a hypothetical system where heat added to the system is 12 kilojoules and work done by the system is 6 kilojoules. To determine the total energy increase of the system, we can apply the first law of thermodynamics, which states that the change in the total energy of a system is equal to the sum of the heat added to the system and the work done on the systems. Therefore, delta E is equal to Q plus W, and substituting this value, we get delta E is equal to 12 plus 6 is equal to 18 kilojoules. This tells us that the total energy of the system increases by 18 kilojoules as a result of both heat and work interactions. A key insight from this example is that the net energy transfer comprising both heat and work determines the total energy change within the systems. The first law of thermodynamics emphasizes that energy is always accounted for, none is lost or destroyed during these interactions. This principle ensures that all forms of energy transfer, whether through heat or work, are tracked and conserved. In any process, we can confidently assert that the total energy entering or leaving a system must balance out, adhering to the conservation of energy principle. By recognizing and applying these concepts, engineers and scientists can design more efficient systems and better understand how energy flows through various processes. This knowledge is vital in fields such as thermodynamics, mechanical engineering, and energy management. Now coming on to the important concept of thermodynamics, and first law of thermodynamics is the energy conservation principles, which is the very much powerful tool and which is derived directly from the first law of thermodynamics. And the principle of energy conservation provides us the energy balance in a systematic way to account for all the energy flows in and out of the systems. Now, what does it say? The net change in a system's total energy is equal to the difference between the energy entering the system and the total energy which is leaving the systems. And that can be expressed as delta E is equal to total energy coming into the system minus the total energy which is leaving the systems. Energy can increase or decrease within the systems, but it is always accounted by this principle, and it is fundamental to understand and analyze this thermodynamic process. Therefore, the general form is equal to delta E is equal to E in minus E out. The energy which is entering the system can be heat, work, mass transfers, or the energy which is leaving from the systems can also be a heat or a work or mass. Okay. Now this equation states that the change in total energy of the systems is nothing but energy which is entering the system minus the total amount of energy which is leaving to the systems, and this is nothing but the energy balance principles, and it applies to all the types of systems and processes regardless of their complexity. It is a versatile tool used in a wide range of engineering problems to track and manage energy changes, whether it is a closed system, open system, a steady state process, or a transient process. The energy balance can be applied to analyze these energy flows in the systems. Now, there are certain key successful applications. Okay. Now, when we want to successfully apply the energy balance, it is essential to understand the different forms of energy. Okay. Now, be familiar with the various forms of energy, including what is meant by internal energy, what is a kinetic energy, potential energy, heat, and work energy. We have to also identify and quantify the energy transfers. We have to accurately identify and quantify all the energy transfers which are there transferred to the systems and coming out of the systems. This may involve measuring the temperature, pressure, flow rates, work input, and the heat losses. For that, we can use the sophisticated instruments for measuring purpose. By mastering this energy balance, engineers can design more efficient systems, optimize the energy use, and troubleshoot the energy-related problems.